Welcome. Today we are exploring a breakthrough at the intersection of deep learning and symbolic logic, the Boolformer. Traditionally, we have faced a binary choice in AI. Do we want the lightning fast pattern matching speed of deep neural networks, or do we want the human readable precise reasoning of symbolic algorithms? This slide represents that bridge. On the left, you see chaos. Raw binary truth tables data appear as nothing more than a wall of zeros and ones. On the right, you see the tapestry, a clean functional logic circuit. The Boolformer is designed to bridge this gap, performing symbolic regression to directly predict a Boolean formula from raw data. Unlike standard models that merely approximate a function, Boolformer aims to discover the underlying blueprints of logic, turning noisy observations into human readable causal rules. To understand why Boolformer is necessary, we have to look at the compromise of modern computation. As shown in the table, standard transformers are incredibly fast, operating at O of 1 inference speed, but they're essentially a black boxes. They excel at memorization but struggle with out of distribution data and provide zero interpretability. On the other hand, classical symbolic regression, often powered by genetic algorithms, provides high interpretability and exact rules. However, it is painfully slow because it relies on iterative searching rather than direct inference. Boolformer shatters this trade-off. It offers the inference speed of a forward pass while delivering compact, exact symbolic expressions. Crucially, it demonstrates massive scalability, generalizing to functions with up to 120 variables, far exceeding the limits of traditional symbolic search methods. How does it work? We treat symbolic regressions as a sequence to sequence problem. The input is the raw material, a truth table where each row is a sequence of input variables and their corresponding output. This high dimensional data is compressed into a single high density token vector. The engine under the hood is a transformer with 60 million parameters and 16 attention heads. It was trained entirely on synthetically generated Boolean trees. During inference, the model doesn't explicitly calculate the math. Instead, it observes the pattern in the truth table and autoregressively infers the structural blueprint, decoding it into a symbolic expression like and x1, not x2, a reverse Polish notation. This decoupled execution means the model is learning the grammar of logic itself. A major challenge in learning Boolean functions is the tendency of neural networks to overfit. Standard networks often create overly complex Fourier spectrum interpolators that work for the training data but fail on anything new. Boolformer is designed with a mean degree bias, but it is trained specifically via algebraic simplification to output the shortest possible circuit. This is essentially an attempt to solve minimum circuit size problem, or MCSP. For example, when presented with a 10 variable comparator, Boolformer can find a highly compact 17 gate expressions that capture the fundamental law of data rather than just memorizing points. This preference for simplicity is what allows the model to generalize so effectively to unseen data. In the real world, perfect truth tables don't exist. Data is missing, corrupted, or buried under the mountains of irrelevant information. This slide highlights the Boolformer's resilience to that. The model can endure a 10% random bit flip rate in truth tables, which is a lot, 10% flip rate, and still recover the correct logic. Even more impressive is its ability to handle data sparsity and irrelevant variables. It can find a core functional rule involving 6 variables even when the signal is polluted by 120 irrelevant variables. Furthermore, it can function while observing only a tiny fraction, sometimes just 30 to 300 points of a massive multidimensional hypercube. It isn't just learning logic, it's learning how to filter signal from noise. We we put Boolformer to the test on real-world datasets from the PMLB benchmark. The core argument here is that Boolformer provides interpretability without a performance penalty. As you can see, Boolformer matches the accuracy of a 100-tree random forest with an average F1 score of 0.89 to 0.92, but there is a massive difference in the output. While a random forest is an ensemble of hundreds of trees that no human could reasonably parse, Boolformer delivers the same results as a single perfectly legible formula. For instance, in the mushroom toxicity dataset, it doesn't just say a mushroom is poisonous. It gives you the specific logical rule involving gill size and stalk root that determines the toxicity. One of the most exciting applications for Boolformer is in computational biology, specifically in mapping gene regular networks or GRNs. Inside a cell, behavior is governed by a dynamic Boolean network where the state of one gene activates or inhibits another. Mapping these networks is notoriously difficult because biological data is often noisy and low signal. Current state of the art method relies on evolutionary algorithms, which, as noted here, can take hours to map just a single network. This creates a massive bottleneck for researchers trying to understand complex biological cascades or disease pathways. This slide shows the dramatic performance shift. By using Boolformer, we can evaluate each gene independently through a single forward pass. Look at the comparison. Traditional genetic algorithms like Gabni or Mibni might take over 6 hours to solve a network. Boolformer achieves similar or better results in just 5 seconds. It matches the accuracy of these SOTA methods but provides a speed up of several orders of magnitude. This isn't just about saving time, it's about enabling a scale of analysis that was previously computationally impossible. We also wanted to know how the model understands its functions. By looking at the attention maps, we found that the model isn't just memorizing, it's learning structural geometry. For example, when mapping a 4-digit multiplier, the attention heads independently discover block structured symmetries, what we call the checkerboard. When solving complex parity functions, the heads perform an anti-diagonal comparison, explicitly comparing antipodal points across opposite ends of an n-dimensional hypercube. This proves that Boolformer is developing internal representations of logical structures that mirror the way a human mathematician or engineer might approach the problem. In conclusion, whether we're determining the toxicity of a mushroom or mapping the biological cascade of human gene, the objective of science remains the same: extracting concise causal rules from noisy observations. Boolformer is more than just an algorithm, it is a universal translator for scientific discovery. It takes the chaos of raw data and spins it into the natural laws of logic at the speed of a single forward pass. As we move forward, this capability to provide both speed and interpretability will be essential for AI to act as a true partner in the scientific process. Thank you.